Hello, everyone. Welcome to another session of the AI for Net Zero webinars. My name is Amin Zare. I'm research fellow at the University of Surrey and today's chair. I have today's chair. I'm delighted to have two early research career from Imperial College and Exeter that can give us a lecture. First of all, Dr. Ivis Kerama. He's a postdoctoral fellow in the Imperial College and applied modeling, and he has computation in the computational group. He is a specialist in computational method for multi-physics modeling of the urban flows, indoor air quality, and multiphase flow with the applications to the environmental and chemical engineering. His research interests includes high fidelity modeling, data assimilation, and machine learning. He works with other researchers at AMCG, if I say it correct, to develop the rapid AI-based partial differential equation solver, namely AI for PDEs. So before we start the session, I would like to encourage you guys to ask your question in the comment, and after the talk will be finished, the presenter can ask your questions. So stage is yours, Ivis.
Great, thank you. So hi, my name is Ivis Kerama. I'm working with Ben Youngman and Daniel Williams on the ADRIS project, which aims to create an overall platform and tools for bespoke decision making for planting trees in order to meet the net zero targets and our goals. My part of the work is for the downscaling of climate data, which is getting much higher resolution data than what's available from global and regional climate models, which will feed later on into the emulators we are developing, and in turn into other simulators and an overall algorithmic package and the software package that we are developing here to aid in the decision making of exactly where to plant trees, given specific goals, and so on. So here I will just start with like a very simple overall framework for modeling spatiotemporal processes, and we'll see how that sort of feeds into downscaling of climate data. So on the left-hand side, you can see sort of a blocky, stylized picture of the Earth, and you can imagine that as sort of a global climate model. Although, of course, the atmosphere is going to be above the Earth's surface, but it's sort of it's a good visualization of how sort of blocky and how large the resolution is. Which you can see, it's almost like an entire country like UK has like only a few tens of blocks. Whereas on the right-hand side, you can imagine a much finer resolution, but which is not available due to computational reasons, and it cannot be sort of simulated with different climate scenarios, for example. So in our case, we will want to focus on UK, of course, but also like be able to go from different climate scenarios, 2.6, 8.5, between those where we don't have like 12 kilometer high resolution data. We have only the 6 kilometer. But overall, we want to downscale even the 12 kilometer resolution data down to meters, so say 50, 100 meters. And in particular, the overall goal of our project, and which we'll sort of develop into the software, is to downscale down to parcel levels. Parcel levels, you can imagine parcels of sort of land of in the order of a few square hundred meters or 20 kilometers. But again, much higher resolution than what's available. So how will we achieve that? Well, again, we'll have multiple climate scenarios which are available in different resolutions for whatever reason. We have multiple ensembles within each scenario. We have different sources of data, and moreover, we have the simulation data from our simulators, the global and the regional climate models, but also we have observations. And we want to somehow combine all of these into one large framework and statistical model, such that then this can feed into and sort of be an overall model for which we can sample from, and then downscale our data to whatever the desired resolution is, down to parcel level. So here, just again, a sort of nice stylized visualization of a random field, which we'll use for our modeling. This is sort of a visualization of a Matern random field as a solution to a particular stochastic PD. The exact form doesn't matter. The point is this, through some brilliant work, has been connected to Gaussian macro-random fields, which Markovian means the precision matrix is sparse, and which allows computations to be done much faster than if you were to do a full dense matrix in the full MCMC approach, which will initially avoid, but then we'll incorporate later on into the parts where we can afford to spend more computational effort. Now, again, downscaling, what do we want to do? We want to go from very low resolution data. You can imagine the bottom grid to much higher resolution data, but that's for like just a 2D plane surface. We can imagine that can sort of extend to higher dimensions, but for now we'll stick to just 2 dimensions, and we'll see how that downscaling sort of can be achieved. Now, just to give you an overview of how it actually looks like. Forget about the colors; they're not really important because they're height, topography. But the 6-kilometer resolution looks like they're on the right, and the 12-kilometer resolution looks like on the left. You can imagine that 12-kilometer resolution looks like it gives enough detail, but in reality it doesn't, because you can imagine if an area is in Exeter, for example, where we are based on, it has only like a few 6 or 7 rectangles, which are not enough to inform any kind of decision and any kind of land surface model that will be used to decide where to plant trees and exactly when. So these are real data from global and regional climate models. The left is the regional climate model of UK of 12-kilometer resolution. The right-hand side is the 6-kilometer data from the global climate model. These are from different scenarios, just to be sure, but for the same day. Now you can imagine that resolutions that we would actually want, see these 2 rectangles, are very coarse. It's basically 1 value or maybe 2 values, which are for all intents and purposes useless for any sort of fine work or land surface models that we need to use daily data, maybe, or even hourly data, and data the resolution of 50 meters, for example. These don't really work. So we can see how we'll go from something that this size, say a 12-kilometer grid box, which is the entire screen now, that has 1 value, to what we actually require, which would be something like this, 100 by 100 meters, 100 times downscaling. So we'll need to somehow infer from 1 value 10,000 values, which might seem sort of a bit ridiculous at first, but the point is that we'll be able to form a statistical model that will incorporate maybe high-resolution topographical data. Maybe we'll have some areas that are satellite data is available, actual observations from certain areas, observations from other areas in the gridded data, maybe a small model that's been run through some other process. And again, in general, like some other data that can all be incorporated, whether they overlap or not, to build sort of an overall statistical model that can also be sampled from extremely fast, and so we don't need to run simulators to do the actual scaling. Or, since it's reasonably flexible, we can incorporate continuously new data such that when any user will want to run a small sort of scale through our software, they will want to make a decision about a very particular kind of area, and then maybe throughout the years they decide to add some data or some weather stations. They can immediately upload their data. The model will take into account the new data, and for their area of interest, which is the important thing, which they need to make decision on, they will be able to, in a very simple terms, reduce the variance around the uncertainty in their area, but overall build a better statistical model that's just for them. So now, again, a simple model. We usually have, like in this case, around 50 climate variables, which we need to downscale all of them. Initially, not in a full joint model, because that's sort of too complicated and creates some other difficulties. So we'll start with a simple linear regression model. Not a linear regression model in the sense that everything will be just some covariates, but just a simple general additive model with some spatial interaction, and some temporal interaction, and some error terms that's independent of spatial or temporal effects. Now, what we actually want here of the overall model framework is to go through X, Y, where X are the values for overall every grid, and ST and S is the value of the particular point. And then we want to go from observations, our observations, which in this case will be the climate simulations, which will be the true latent field in the background plus some error, and we can decide ourselves what our error is, which itself, the true latent field is made of some actual output from the model, and plus some spatially structured error or spatiotemporal structured error that can be anything. It can be Gaussian process, it can be deep Gaussian process, it can be some combination, or something even more sort of structured. The point is, now imagine that W is going to be just the downscale version of the X, which X being our actually data, which can be an effect of some deterministically downscale data. Deterministically means through some very standard techniques, we'll have some high resolution data, which we can treat that. But what we actually want to do is to build a statistical model around that so that we can introduce the uncertainty around every sort of specific sort of deterministic downscaling. In our case, overall, we want to sort of go even bigger, even more sort of overall to capture everything. We want to do that for every climate scenario, but also for climate scenarios that we don't have actually even regional climate model data. For example, the 60 kilometers is only available for 2.6. We want to infer the 8.5 plus some others. Now, how do we do that? Forget about the sort of all the individual letters and particular functions. They don't mean much when you see it overall. But the point is that we have a particular statistical model from which, given climate output simulations from various resolutions of them, 60 kilometer, 12 kilometer, and various climate scenarios, we can build an overall model that we can sample from, so we can get other climate scenarios. And that model, of course, will incorporate, can be sort of a very extremely generic model, as I've written it here. They can have like a normal, some general likelihood, which the priors can be another Gaussian process, can be a deep Gaussian process, can be just a very simple process. But the point is that we'll be able to sample once we have the full joint model. Now, I will just start with a very simple model here, a very simple generalized additive model, which will have a Gaussian random field plus a temporal process, which can be another regressive one here, plus a spatiotemporal interaction. Now, I will start even simpler here because we don't have much time to go through this. It's just a simple spatiotemporal model where the XB, we don't have any covariates. We want just purely to feed the data to some random field to see if we can even simulate from it and if it sort of comes out with data that look like our actual data. So we won't have any additive effect, no fixed effect. We'll just have purely random field, which is the psi here. Now, psi here for this particular model is decomposed into spatial and temporal threads. Now, W is the adjacency matrix. D is the adjacency matrix for the temporal data. You can imagine every point is influenced only by its immediate neighbors and temporally only by the point in the future and the point in the past, just one time step ahead. And sort of just an extremely simple model that we can sort of start looking into how it captures any sort of spatial variability and if it can actually capture anything. So we'll start with some climate data, wind speed data at 10 meters, just one day, just some random day of January, which will have removed the, sorry, this is June, which will remove the mean overall trend, just so you have with no mean effects. Now, again, how will our model look? The true fields on the left, just zoom into a small area. Through this model, we'll get some posterior means, and of course, we get the precision as well. We can sample from, and we can see that the posterior actually captures pretty well some of the major features. And the whole point, of course, is that we can sample endlessly from that. And we'll see how that sort of will inform our later downscaling. Now, to show actually the entire map, the left-hand side is the simulation, the actual output of the simulation from one random day. Through the model, we sample different realizations. Now, the variance here is very small because, again, remember, we're just fitting the model to its, the data to itself, just through the random field. And it reproduces the random field fairly well. But there's, of course, like almost a very small variance in the pattern because, again, it's not getting fitted to sort of high-resolution data yet. Now, overall, what we want to do is to actually sort of make a joint model of and hence infer the distribution over the all climatological variables, initially independently of each other, not jointly, so that we can inform and infer actually the relationship between the high resolution data and the low resolution data. Now, this can be done either through, after the joint model is built, we can just define a grid in an arbitrary resolution and do some kriging, i.e. Gaussian process interpolation, which will have higher variance depending on how low we can get, or we can have, once we have the full model again, we can sample different climate scenarios, and then we can sort of deterministically downscale, but the main difference than just doing the standard dimensional scaling, we will have uncertainty built in because we already have the model. Now, the point is, the final question, I guess, is since we'll have the dimensional scaling in combination with the statistical model of all the climate scenarios that we want, will we use a exact same different functional form? It can be mechanistic dimensional scaling, or it can be sort of any of the modern machine learning approaches to that, which are a lot of them in the past 2 or 3 years. Or do we want to use the same functional form for each point in our sort of area of interest? Again, we'll have a full statistical model for all climate variables for different scenarios, such that we can sample from. We'll get the mean of the field. And then again, we can sample from that field. For every new sample, do we want to get the same exact sort of deterministic transformation to get high resolution data? Or perhaps we want a similar transformation. Perhaps we want overall near the main sort of mass of the distribution, to have only a very specific transformation, a very specific non-linear functional, such that give us like a small range. Perhaps further details, we want different transformation so that we can capture higher variance and higher uncertainty, but also like we don't want to give as much weight to that kind of downscaling. And you can imagine all these functions can be different downscaling approaches. I mean, deterministic ones, since our model is already built. Again, that's sort of more for future work, but for now, the overall aim is to build a fully joint statistical model of different climate scenarios, such that we can incorporate observations, but also lower, high, and low resolution data, again, in a joint model, such that we can sample from, and then can go through the pipeline of deterministic transformation for a specific area of interest for each user, and then build into the pipeline of our overall software package that will sort of go much further in getting all these climate variables into our emulator, and overall decide where and how to plant trees and what's the best strategy for that. So that will be it. Thank you.
Okay, thank you for your presentation, Ivan. Anybody have question can leave there in the comment box, so I can Ivis can see and answer question. Any questions? Okay, I have questions actually. So could you talk about your computational time and how long does it take, and do you need to do some reduction in the computational time? And yeah, and just did you do some simulation in your normal PC, or you need supercomputer for this?
Well, great question. That's exactly the point. Like instead of, again, we don't want to simulate out of these things because they're extremely expensive. So we want to have a statistical model. Even so, statistical models can still be expensive. We want to simulate out of it. We want to do some inference of it. So you can do a full MCMC approach, which to infer the large spatiotemporal model will still be probably too expensive. So for now, we're using a combination of INLA, integrated nested Laplace approximation, and MCMC, with the hope to use full MCMC. But again, just to give an example, for 10,000 grid points and 1 year, so 360 days, that can run in a few hours on my laptop to feed the entire model. Now, a full MCMC approach will probably be too expensive for that if you want to incorporate all the possible spatial points and temporal points. But again, in our case, as I said, the user will be able to select a small area. They can feed the model, they can update their model. So there, they'll be able to use full MCMC approach, which is exact sampling instead of INLA. So we'll have a higher quality estimates. I mean, they will have lower variance in their estimates.
Yeah.
But again, the whole point is for this to run on the user's laptop, because again, we need to, in the end, we'll have a whole package, a whole software suite that every user will want to run. So we cannot expect anyone to run this thing and update the model. That takes a few hours or days. Other parts of the thing can take a few hours, but this thing, the downscaling, has to run relatively fast. Also, just make sure that it's clear this needs to be done once. If you want to update with new data, new observations, that's another thing. But once you've downscaled to some specific area, that's it. So yeah.
Yeah, specifically, you also mentioned that you need to deal with stochastic parameters. So again, that increase computational time.
Yeah, exactly.
Okay, thank you. Any other question? If not, I have also another question. Oh yeah, that's a question. Is this work related to the weather or climate? And how do you validate this approach?
The first question, yes, because we're downscaling climate data. Although downscaling is also used for meteorological observations, which are much more fine. But again, the verification and the validation approach works as with any sort of statistical model. You subtract data from your dataset, you partition your dataset into validation and training dataset, and then you validate on the validation points. So you remove 10, 20, 30% of your data, and then you try to see what are the predictions on points, given observations, and see how close the model predicts them. Now, first of all, like what I showed, like the first thing you want to do is to see if your actual model can reproduce something that looks fairly close to your overall spatiotemporal field. Then again, once you've downscaled, you want to see that one day ahead, because it's like you can downscale. You would want to downscale not just for historical data, but also for the future climate scenarios. So you will want to, at least for now, that you can validate from, you will want to see if the downscaling is close enough to actual observations. That's another validation. But since you have a fully Bayesian hierarchical model here, you can easily validate that, since you can calculate the mean posterior predictive, and you can see what are the samples from that. Are they close to actual observations at an arbitrary resolution? Since you have the full model, you can sample from it arbitrarily.
Thank you. Any other questions? If not, I think we can pass to the next presentation. Thank you, Ivan, for your talk. And
thank you. Thank you for hearing me.
Sure. So for the next presentation, we have Dr. Boyang Chen from Imperial College. His expertise is applied modeling and computational at AMCG Group. He specialized in computational method for multiphysics modeling for urban flows, indoor air qualities, and multiphysics flows with applications to environmental and chemical engineering. His research interests including high fidelity modeling, data assimilation, and machine learning. He works with other researchers at AMCG to develop a rapid AI-based partial differential equation solver, namely AI for PDEs. So, floor is yours, Boyang.
Okay, yeah. Thank you for the introduction and the invitation. So yeah, today I would like to present our recent research, which is focusing on solving the PDEs, mainly like multi-phase equations on structured meshes using AI libraries. So I'm going to give you a general description of for the new method, and then showcase some results that we have been working on for the engineering applications. And before doing that, I would like to thank for several consultants supporting this research. So yeah, I would like to start my presentation by showing the methodology that we used in this work. We call it as AI for PDEs, and the key idea of that is to design ways in the neural networks based on the discretization of the PDEs instead of training the data by using AI surrogate models. And essentially, this approach can provide the exact solution of the PDEs on unstructured meshes by comparing with the traditional numerical approach. And you can see how it can be used to predict the flow past PDEs and generating the very detailed turbulence surrounding it. And basically, we have there are several advantages that we have been mentioned based on this new approach. Since the code is written by the PyTorch, which is massively optimized and easily allow us to run any code on GPUs or AI computers. So the new code is pretty faster than the traditional ones because the GPU is much more powerful than the CPU. And in addition, the code can be effectively incorporated with the existing AI surrogate models, in which case we can differentiate the AI models and perform the data simulation and uncertainty qualification, and also as well as sensitivity analysis. And we are hoping this new method can be supported by the AI communities, like the OpenAI company. And go to the next slides to look into the more details. I can explain the main structure that we use to establish AI for PDEs, which is the convolutional neural networks. And it can be elegant with the GPUs and any AI computing architectures. And the reason why we want to use these structures is the CNNs can represent the discretized stencil on structured meshes. And based on the different numerical schemes, for instance, phonetic difference in phonetic element and phonetic volume schemes. So the example I put on the top top right is showing how it works. So basically, we can consider the left figure is an input of the neural networks, and the filters showing in the middle is determined by the central difference in schemes, and the output is showing on the right hand side, which can be made by passing these filters on the initial image. And the another benefit from the CNN is you might be realized that we can easily implement the multi-grid algorithms using the convolutional filters by reduce the size of the input size. So as showing at the bottom, so in which case we can restrict and prolongate the residual and calculate that between the different grid levels. Well, so in this section, I will show how the AFLPDs can be used for solving some classical safety problems. So as showing on the top right, the general structures is used to solve the pressure and the velocity coupled field. And the input of this neural network can be considered as the variables at the current time levels, and the output can be the same variables, but at the next time level. And additionally, the bottom right figure is showing the U-Net-based structures, in which case we can implicitly solve the pressure field. And in order to discretize the Laplacian operator in 2D, I would like to give some examples in here. So, for instance, we can use the phonetic difference method, and all the values in here is determined by the numerical schemes instead of training data. And alternatively, you can try to use the phonetic element method, and all the variables are pre-training by the numerical scheme. And after establishing the AI for PDE solvers, I can show some examples or results of solving the scalar transport equation. like showing here, that is the governing equation, which is a PDEs, and we initially distribute the two sources in the middle, and then use the determined convolutional filters to propagate the source with the time. So eventually you can see the result at the different time levels, and the number of the time levels means how many times did you pass the filters on the initial image. And the left figure is showing some examples. Here is the element nodes, and the green boxes. The green box is representing the 3x3 convolutional filter. And go to the next slide. I would like to show another applications of the AFLPDs to solve the 2D flooding problem, which is based on solving the shallow water equations. And in this case, we are focused on the flooding event in Carlisle 2005, and the details are indicated in the right-hand side, including some water source and the sampling points. And the animations you are looking at on the right-hand side is the simulated water level for 68 hours real time, which are mainly from the three water sources as highlighted in this diagram. And to validate our new models, I'm just showing the time histories of the water level at the 15 sample points, which are mentioned in the last slides. And the comparison of the numerical result by AFLPDEs with the observation data, you can see showing a good agreement in terms of the water depths. And besides, the right-hand side is presenting the spatial variation of the water level at the 4 different time levels after the flooding. And for these slides, I would like to extend the applications to the 3D fluid problem instead of the 2D or scalar transport equation. So for instance, we applied AFLPDs to solve the air flow in the South Kensington area, where our campus is located at. And the left figure describes how the simulated area looks like. And the right animations is showing the speed of the airflow, which is initially coming from the left to the right with the speed of the 1 meter per second. Since we have parallelized the AFLPD's code, and we are running the simulation with multiple GPUs. For instance, we can run like A100 GPUs. So we create 2 billion element nodes for these simulations with 1 meter match size, which can, in theory, allow us to have a very detailed street level turbulence within the lots of buildings in the South Kensington area. So to handle this more complicated flow problem, we apply the AFLPDs to solve the multiphase flow and fundamentally simulating the collapsing water column case. And the two bottom figures are showing the basic setup of the flow problem, and the middle one is presenting the indicator field, which can be used to differentiate the interface between the air and the water. And the results are showing here for 6 different time levels. And the left figures showing case the isosurface of the water in the 3D, and the animations is showing the time evolution of the isosurface, which are representing the interface between the air and the water. And also that red figure is showing the validation of the propagating speed by comparing with our numerical results with the experimental data and other numerical research. And all the results showing here have been published in our recent paper, which I will highlight in the end of my presentation. So in case you would be interested in looking into more details for this work. So next, by using the same multiphase code solver, we apply it to solve the 3D flooding problem, the same problem that I mentioned in the previous slide, but we will compare it with the 2D model that we have showcased before. So in this case, instead of discretizing the problem as the shallow water equations, we are considering the problem as the water and air coupled system. So the result showing on the right-hand side is the spatial variation of the water level covering by 10 hours after the flooding, and also we made like the comparison between the 2D shallow water equation model and the 3D multiphase models with different mesh resolution in the vertical direction. And the comparison indicates a similar result for both models, like the 2D and 3D numerical models. And to touch with more like the real engineering applications, we are currently working on the cross-media flow, which will happen in the lots of cylinders in a tank. So we are hoping such simulations can contribute to the engineering design in terms of storing carbon dioxide and saving energy in the real life. Regarding the simulation details, I just put some grid size and the domain size in here, so you can check the details of that. And also, we use the same multiphase code, but incorporating with the surface tension model to account for the interaction between the three different phases. And we consider the physical scenarios like the air will be injected from bottom to the top into the water. So basically, there are three phases: air, water, and the solid in this simulation. So based on the numerical setup, I'm just showing the result I'm showing here is for the flow speed in the tank at the different karting surfaces. So you can see very detailed flow structures, which is happening on the between the gap of the lots of cylinders in the tank. And besides, I'm also showing the indicator field in the tank, which is ranging from 0 to 1 to visualize the interface between the air and the water, which are between the lots of cylinders as well. So based on that result, I would like to take a short summary and conclusion for our recent research. So our new approach, namely like AI for PDEs, has been validated to predict the flow dynamics by comparing with the observation data or other numerical results, such as the shallow water equations and the single phase and multi-phase flows. And based on the successful validation, we try to make some demonstrations based on that new method, which can be applied for a wide range of the fluid problem. For instance, the collapsing water column, urban flow in the city, and cross-media and 2D and 3D flooding problem. And based on the result we have got from this new research, we found several advantages. So for instance, the flexible for this code, because the code is just written by the Python language, which can be easily run with any computing architectures like CPU, GPU, or even new AI computers. And the another big advantage that we found is the speed, because as I said, mentioned before, the GPU is much more powerful than the CPU. So the speed of the new approach is pretty faster than the one we have been used. And these advantages can contribute to the digital twin or real-time prediction in the future, and also in which case we can perform the sensitivity and the optimization based on the data set generated by the AFLPDs. And also because the PyTorch is massive supported by the AI company or AI teams, so the AFLPD's code is relatively easy to implement, and also it's very friendly for the developers or the users to use and develop the code further. And apart from what I'm showing in my presentation, we also work on the several different applications by using AFLPDs. So for instance, we are apply the multiphase code to simulate the RT instabilities, which showing the very details between the very details in terms of the interface between different phases. And recently, we also successfully implement particle modeling in the AFLPDs, which can allow us to run some two-phase flows which can be applied to the chemical engineering, such as the fluid dye simulations. And to make more applications to the single phase flow, we also apply that to simulate the airflow over the vehicle, showing the very detailed flow dynamics surrounding the vehicle. So eventually I would list all the recent publications associated with this new approach, and we have made the piece of AFLPD's code public. So I put the GitHub link to the AFLPD's code in case you want to give it a try. And yeah, and thank you for your time.
Thank you for your presentation. Well, that was really interesting and fascinating. How you can decrease the computational time. Anyway, we have some question and would appreciate if you could answer it. The first one is here. Do you predefine the number of multi-grid iteration, or you use residual criteria for conversions? And are these simulations done in a single or double precision?
Okay, so the first question, so the number of multi-grid iterations is highly highly depending on how difficult do you want to run the safety problem. So we can just tweak the number of the multi-grid iterations to stabilize the simulation. And for the next question, so all the PD's code currently is using the double position for all the spatial for all the spatial derivative of the PDEs.
Okay, thank you.
Yep.
And we have another question. In your parallel solver, do you divide this domain into the subdomain where each subdomain is a single GPU? If so, how do you perform this communication between the subdomain boundaries?
Okay, that is a good question. So for the parallelizations, we have implemented a message, like MPI, message passing interface technology in the AFLPDs, which is just based on some PyTorch packages, which can achieve the halo updating between each subdomains. So based on that code, we can easily run the AFLPDs with any number of the GPUs that we want to
run. Thank you. Any other question? We still have time. If any question come up, we can answer it. Meanwhile, I have another question. Since I'm a bit new with this AI modeling, I just have some time series deep learning. So I was wondering, this time, how much does it take to say that, okay, it's enough, you don't need to go further for simulation? 1 hour, 2 hour? What's the factor that, I mean, based on which factor you can say that it is good enough?
Yeah, so it depends on the type of the fluid problem that you want to simulate. Because if you are trying to produce some fundamental fluid problem, so you will have some benchmarking result that you can be used to compare with your the results generated by your new model. But if you are just want to run some real applications, you might be compare the result with the observation data to say whether your simulation is perfect or still need to make some improvement on that.
I see. Thank you.
Yeah.
We have another question. Yeah, thanks for parallel parts. Do you perform a special padding at the boundaries?
Yes, it is, because the theory is for the convolutional, like for the AFLPD, is try to make sure the input size of the convolutional neural network will be always same as the output size. So we have to create the padding layers for any input tensor, and then we can impose the boundary, like physical boundary conditions on the padding layers. So yeah, it is necessary to perform the padding layers on that.
Thank you. Thank you for your answers. So we still have time. Yeah, we're a bit ahead of our plan. If there is no other question, we can, we can just wrap the session. And thank you for your talk. Yeah, hope see you next week as a listener. Okay. Thank you everyone for joining us in this session, and hope we could see you next week for the next webinar. Yeah, see you next week.